So yes, I slightly changed my the title of my talk because I realized that some of you were disappointed that I would not talk about simulations with the classical computing. That's why the classical is between quotes. Okay, so of course, one of the existential questions that we ask ourselves as physicists is, where did the elements come from? How did we get here? How does the universe evolve? And personally, I subscribe to these existential questions. This has always been something that has fascinated me. And reactions between nuclei play, of course, an important role to answer these questions. From the Big Bang, reactions to the reactions that happen in low mass stars like our sun. And then, of course, the reactions that happen in heavier stars like giant and supergiant stars that produce the chemical building blocks of life that are carbon and oxygen. And of course, there are the other reactions that produce the heavy elements that I'm not talking about right now. But so today, in the interest of time, I'm focusing on the PP chain reactions, and in particular, I picked the beryllium-7 P gamma reaction rate, which plays an important role in determining the flux of neutrino that comes from the sun and that we can directly detect here on Earth because they are high energy enough that we can detect them. So, of course, this reaction is very important, has been measured many, many times over the years, but and you can see here the experimental data, but the issue is that the Coulomb repulsion between the proton and the beryllium-7 is such that on a laboratory setting, it is really hard to go to the very low energies that are required for solar models, which are, I show them here, are just a few hundred electron volts, kiloelectron volts. And this is because, of course, you have very low counts. Okay, sorry, let me, I skipped this part that is important. So the nuclear cross-section at the very low energies is basically given by what we call the astrophysical S factor, that really is the nuclear contribution. And then what you can see here is this other part is parameterizing the Coulomb contribution that comes from the fact that basically to fuse the proton and the beryllium-7 have to tunnel through the Coulomb barrier. And that suppresses the cross-section enormously at low energy, and therefore, this is what happens. So what happens is then that we are forced to use theory to extrapolate down to the energy that we are actually interested in. And if one looks at the recommended value right now for the S factor at zero energy, this is what is recommended right now. But I want to point out mostly is the error bars that are associated with this recommendation, the experimental one, but most importantly, the theoretical one that comes from this extrapolation is actually the largest and the one that dominates. And these uncertainties are still, they still play a major role in solar model simulations. So we want to bring them down. What in our, what I do in my research group and collaborators is typically to try and compute this type of reactions ab initio. And what I mean from that is from the nucleus degrees of freedom and as predictive or as high fidelity as possible interactions among the nucleons. And what we do lately is to use nucleon and trinucleon forces that have been derived within the framework of chiral field theory and use those in many body calculations of the reaction process. Now, of course, many in the audience can say a lot about all the controversies that are related to these forces. I am just a messenger. Don't shoot the messenger. But other than that, so this is what we do. So let me say just a few words more about the method, the many-body method that we use. So we use these ansatz for the many-body wave function, in which there are two terms. So we use an expansion in harmonic oscillator basis states, if you like, many-body harmonic oscillator basis states, to describe the static property of nuclei, and we use it to describe the wave function of the composite system, so the proton and the beryllium-7 when they are close together. And then we also have an expansion on microscopic cluster states that describe, in this case, although the drawing shows an alpha particle there, in this case is a proton in relative motion to the beryllium-7 core, in which our beryllium-7 core is also described microscopically and ab initio through this type of expansion. Okay, and we call this approach no core shell model we continue, because this is it's a child of the shell model, except that we really don't have a core. We treat all the nucleons as degrees of freedom that are active. So clearly, this part of our ansatz, which is given by static solutions for the aggregate system, describes when all nucleons are close together, and then we have these continuum microscopic cluster states that describe when the projectile and target are separated. So they're very important, of course, at the beginning of the scattering process and at the end of the scattering process, also to describe our asymptotic states. But so this is the setting. So now, lately, Kostas Kravaris, who works in Livermore, and he used to be a postdoc working in my group, and now he's a staff and continue to collaborate and work together. He applied this approach to predict the beryllium-7 P gamma capture rate, and he carried out calculations with a whole zoo of possible chiral nuclear and trinuclear forces. The nomenclature here is a little bit, Byzantine and brief, but let me, for those of you that in the audience really want to know what these are exactly. So these first three are the nuclear interaction of Enten, MacLeod, and Nozick from 2017 up to Order and Forelot, and they are combined then with the trinuclear force at N2LO regularized with the local non-local regulator, which I actually, I fitted the parameters of this trinuclear force in a paper where we did also uncertainty quantification for an alpha scattering. Then there is, once again, this an interaction combined with a trinuclear force that, however, right now contains also a subleading term at N3LO that was derived by Ghirlanda to include additional spin orbit interaction in the trinuclear force. And this was also adjusted by us, the Kavli constant. And then we have I will say the older N3LO and then potential from Enten and MacLeod from 2003 with, again, both now a local and non-local trinuclear force. So these are this kind of nomenclature. So now, in general, what happens is you can see here, all these interactions tend to give a slightly different description of the system. When it comes to the so when it comes to the these are the S-wave scattering length of the initial scattering state between the proton and the beryllium-7. We have, this is a couple channel calculation. We have two channels in which the proton and the beryllium-7 will couple in either a spin 1 and a spin 2 configuration, and so these are the value that we obtain, and they have opposite signs, and for what was this that is quoted here are, let's say, empirical values that were extracted through an hermetrics analysis, so a little bit of a mix between experiment and theory. The good news is that at least we get the same sign, but you know, I wouldn't extrapolate much more than that. And these are the asymptotic normalization constants of the boronate wave function that is the final state of this capture process. And they, again, we have a couple of channel calculations. These are the boronate ground state is mainly made, let's say, of two configurations in which the proton and the beryllium-7 are in a p-wave relative motion. And once again, we get, in this case, you know, somewhat close result with this empirical determination. So now let's turn to the S factor. And as I was saying, you know, you change the interaction, you get somewhat different results. So what do? You throw your hands in the air. So let's give a look at here. We have this blue curve, which corresponds, let's say, to the somewhat from the 2003 interaction. It agrees well with this experimental data from Huygens at low energy and in the peak, but then when we go at higher energies, it seems to you know, be discrepant with respect to this experimental of Huygens. So then we have this other interaction that is the newest, let's say. This one, you know, you could say, well, it also agrees well with data because data are discrepant and well in the peak, and maybe it also reproduces the higher energy resonance here. Actually, I didn't mention, this is a 1+ resonance, and this is excuse me, yes, a 3+ broader resonance. And the capture mechanism progresses mostly through any one transition, electric dipole. And then this is a transition due to a magnetic dipole and this to a quadrupole. But okay, so this is the situation. However, it was noted already by Daniel Phillips, excuse me, before Daniel Phillips, already by Daniel Bay, and then it was taken also by Daniel Phoenix, that if we then look at the calculated S factor at zero energy as a function of the calculated sum of the squares of the asymptotic normalization constants, one can find that they obey a linear relationship, which could help you to extrapolate to zero energy the S factor if you could measure these accurately, but that's hard. So what we did instead, and I should say what Kostas did instead, is to look, okay, so what does it happen if we plot this zero energy S factor that we obtain with these various interactions as a function of the S factor at the finite energies, for example, 250 kiloelectron volt. And so what one finds is that once again, there is a somewhat linear relationship between the two. Is not exactly, you know, linear, maybe, you know, to be general, we used a low order polynomial here, but one can still find this sort of correlation. And what are shown here, these various calculations, and associated with them are error bars that are related to the order or the chiral expansion. Okay, so they were estimated compared to the order of the chiral expansion. So, for example, calculation N2LO has the largest error bar, while calculation at N4LO have the smallest error bar. And so one can do a fit like that. And so what this means is that then one, you know, there are these correlations. So what else can we do after we do this? Well, then we can utilize this sort of universal behavior that has been identified here to see if we can use it to extrapolate the S factor to zero energy. And so one can take the experimental data that are available, for example, the S factor, I don't know, measured by Huygens at 250 kiloelectron volt. Let's suppose that it was, I'm not sure, 22 electron volts per barn. So I can then go on this on this regression line that was obtained and find what is the corresponding S factor at zero energy. Okay, so one can one can do this game with all the experimental data. And then you can repeat the same game at other energies. So what is shown here is now the zero energy S factor. And here are the various energies of the experiments. And this is, you know, the obtained zero energy S factor for all these experimental data. And then one can do a regression of this data and obtain the S of 0, okay? So this was a little bit complicated, so please ask questions if needed. But the point is that what one finds, so this is the current evaluation. This has very large error bar, as we mentioned. This is experiment and this is theory. And through this process, one can actually reduce dramatically the, substantially, I should say, the uncertainty by utilizing this, let's say, universal correlation that has been identified. Also interesting is the fact that if one considers all experimental data without taking into account their correlation, one gets the results that are shown here in gray. But if instead one considers that experimental data are going to be correlated, particularly if they are a closer energy, so then we obtain this evaluation here, in which basically what we did for simplicity was to weigh each experimental datum by the number of, each experiment by the number of points that it had. And if you do that, you get a less biased evaluation that is here. So the new evaluation is in agreement, with the previous one, except that the error bar is smaller. Okay, and this is actually the result for those that are curious. Okay, so I think I should move on. So I wanted just to say this was an example, but this method has been applied for many other like ion reactions, and I just wanted to briefly call your attention to some of the latest results. For example, this is the helium-4 capture cross-section that is important for Big Bang nucleosynthesis, and it was also computed with the nuclear and internuclear forces. This is the work of Chloe Hepburn in collaboration with our group. And then we also, and I should say Costas, once again, he also computed alpha-alpha scattering with chiral nuclear and internuclear forces that is important for helium burning. And then just in the interest of the context of the conference, I felt that I should say that this method, I also extended it to treat ternary halonuclei and ternary dynamics and clustering phenomena. In this case, rather than having a binary microscopic cluster state, you can have a ternary microscopic cluster state, and then, for example, this, describe the dynamics with hyperspherical harmonics or Fadeev, depending of your preferred approach. And I did in the past apply these to describe the helium-6 Borromean nucleus and also its scattering states. Okay, so I want to give credit to people that really deserve it. And so this is the, let's call it the ab initio theory group in Livermore that works with me. As I mentioned, Costas is really, the person that has done most of these calculations, and it's somebody to really keep in mind for this community. And then I also showed calculations from Chloe. Chloe is a Efimov theory fellow that came to do her fellowship in Livermore. And then, of course, we have our collaborators, Guillaume and Peter. All right, so these were ab initio calculation of light nuclear reactions. We are very excited about them, but let's be honest, it's kind of hard to take our approach and push it all over the nuclear chart. Ideally, we would like to describe dynamical processes that go much farther, in nuclear masses, and we have a hard limitation due to the fact that our calculation will scale exponentially with the number of particles on a classical computer. And I always have here something like this. I put these sticker shock kind of numbers with the Guillaume when we did the polarized diffusion in in 2019, that took us 200 million CPU hours on the latest supercomputer that we had, and things are getting even, more expensive. But so an alternative is that, quantum computing could actually allow us to describe all these processes, because due to the superposition and entanglement properties of qubits, then this type of calculation should scale linearly or at least polynomially with the number of qubits. So that's an exciting prospect that we would like to, consider. So now, as you all know, quantum computers perform calculations by manipulating quantum states, and obviously the qubit is the quantum analog of the digital bit, and quantum gates, which are unitary operations, are the quantum analog of Boolean logic. Okay, and a quantum algorithm is nothing else than a concatenation of unitary transformations on a quantum state. And of course, I put here this classical NOT gate, but of course, for a qubit, the NOT operation will actually flip the qubit, not just negate it like that, but okay. So the physical realization of a qubit, there are many, but here I am presenting the one that I've been working with, which is the transmon. And a transmon is basically a quantized circuit, which is, let's say, a cousin of the LC circuit. Classically, an LC circuit basically behaves like a classical harmonic oscillator, and it can be quantized, and in that case, it becomes a quantum harmonic oscillator. But then, if one replaces the inductance with something that with a Josephson junction, which is basically a nonlinear inductance, then one obtains an harmonic oscillator. And so basically this is what a transmon is, and this can be described by a very simple Hamiltonian. And now if and why let me just comment on why it is important that this be a slightly anharmonic oscillator. That is because with quantum bits, when you have the states, if you want to control them, you have to be able to recognize them. So you need to have, you need to be able to populate them with different resonant microwaves with different frequency. Otherwise, you don't know what you're what you're getting into. Okay. So now, if one is able to control a system like this by suppressing excitations to the higher states, then one obtains a two-level quantum system, which one can use as a qubit. So in alternative, one can actually just use all the Fock states that one obtains in the anharmonic oscillator and work with with what is called a D-level quantum system, or sometimes qudit. And and one can just utilize the underlying Hamiltonian of this system to then drive all these states. And if you, for example, are using 4 levels, this is the computational equivalent of 2 qubits. So you can either work with these Fock states, 0, 1, 2, 3, or think of them as 2 qubits. And what I'm showing here is the superconducting cavity technology that has been developed in Livermore by my colleagues down the road. What I'm showing here is also an image of the 4 states populated that has been taken by my colleagues. So you can see here the 4 qubits. Excuse me, the 4 states of the 2 qubits. Okay, so now this is that was a physical representation of a qubit, and then now how are physically quantum gates? How are they implemented? Well, quantum gates basically, at least in the specific case, they are realized by making the system evolve under the irradiation of some resonant microwave pulse. Okay, and so in practice, how are these microwave pulses determined? Well, what is done is the following. You want to realize a certain unitary transformation. What you do is to basically solve the time evolution of the quantum device, knowing it's unperturbed Hamiltonian, and then this is the interaction Hamiltonian due to these microwave pulses. And then you can optimize these microwave pulses to obtain the unit, so that the overall unitary transformation that you have obtained within a finite amount of time reproduces the within a certain accuracy the unitary transformation that you wanted. And okay, so that's exactly how it is done. So now, what can we do with quantum computers? Well, the easiest thing is to do real-time evolution, right? So it's really good in principle to do time-dependent scattering theory, because you can, we can relate the interacting scattering states with the non-interacting ones. So basically the asymptotic solution where the two systems are far apart and are not yet interacting through the Moller operator. And these are nothing else than unitary time evolution operators. Okay, so great. That's perfect for quantum computing. So now, so you can imagine the following algorithm, which consists in preparing your quantum system in the asymptotic state, asymptotic initial state, make it evolve in real time with the Hamiltonian system, and then looking at the occupation probability of the asymptotic final state. So to do a scattering simulation, then there are two main components: real-time evolution and state preparation. Okay. However, there is always a but. So what's the challenge? The challenge is to actually realize some useful quantum simulation right now with what most people will call the early vacuum tube era of quantum computing. And the issue is that, you have all these great cloud computing, IBM, Google, all these systems. And what they do is to give you a high-level abstraction, sort of like black box, of a basis of elementary unitary transformations that then you can use to build the unitary transformation that you really need, okay? But unfortunately, because there is, what happens is that as you do a dynamic simulation and you start, piling up your unitaries, as you go across unitaries, you're accumulating error and decoherence. And so just like a Jenga tower, the more blocks you add, the more the whole thing is going to collapse. And that's exactly what happens. So for example, this is a per production simulation that was done on IBM, and you can see how just after very few steps, the whole thing collapses to the decoherence point, and the simulation is not really useful. But so in the near term, this is really a self-inflicted problem, because the truth is that you can build, you don't need to use this black box approach and approximate your unitary with these basic quantum gates. You can just compute it. If you know the Hamiltonian, if you now have a clear box and you know what system you're using, you can just find the optimal pulse that will reproduce the unitary that you want. And so that's the approach that we have been using. And so once again, this is the image, and what you can get is an analog digital quantum simulation. And so now, okay, I don't know. So now, what did we do with this? We looked at the scattering of two neutrons, and we did it with the nucleon-nucleon force at leading order of chiral effect field theory. Just I want to reminder that there is pion exchange, it has tensor force, but briefly this interaction as this Hamiltonian has both terms that depend on the spin that I'm showing here, and terms that do not. They only depend on the spatial coordinate. So approximately we can write the evolution operator for a short time step as the product of these two operators that evolve the spatial part and then the spin part. And so then one can consider to have an algorithm of this kind in which we repeat this short-time operator to do our scattering. So now, for the time being, at first, what we did was just to say, okay, let me freeze these nucleons in space, and I will just look at the dynamic of the neutrons for a particular coordinate. This is how we mapped our two-nucleon system to a system of 2 qubits. And here are the results of our simulation on the Livermore quantum testbed. I mean, you will ask me, why should I be impressed? You should be impressed because the simulation that I showed you earlier, the one that was collapsed into the decoherence, was basically a single, it was not even half of a full, I cannot say the word right now. Anyway, so here we do upwards of 420 steps, and the simulation still survives. And more interesting than that is that we took, oh, sorry, I forgot to mention, this is what is shown here are the occupation probability of the qubits as time goes. And so now we can take the Fourier transform of that signal, and then we can even extract the eigenvalues of our simulation. And so this is something that you could not do if you are not able to make it propagate for a long time. I will just say that one can do scattering by reintroducing the spatial part through a quantum classical type of algorithm, in which you can do sort of like a tag team with a classical computer. We have explored that. But finally, just very briefly, the other element that you need is to do quantum state preparation. And that can be done, for example, with adiabatic evolution, when you switch slowly between an Hamiltonian of which you know how to prepare the ground state very well to an Hamiltonian that is your target, okay? We looked into this, and once again, this is a transformation that you can do with small time steps and a quantum circuit. And okay, so here are the results that basically comparing to what happens on IBM, where you get a very dismal 70% accuracy of your evolved state. When you do custom gates, you can get almost to 100%. So this is the end of the talk, just the team and the people that really did the work. And this is just publicity for the GFP APS group that I hope you all will become part of if you're not already.
Thank you, Sofia, for the nice talk. So,
all the quantum Monte Carlo calculations are done in imaginary, in Euclidean time. Is there a way to convince the quantum system to take the Euclidean time?
Yeah, actually, Francesco Turro, a student who is now graduating any day, if he has not yet, of Francesco Pederiva, we collaborated, and he actually has a paper on quantum algorithms for imaginary time evolution. It gets a little bit complicated. You need to, because that is not a unitary operator per se, you need to be clever and find a unitary operator that if you take with an ancilla qubit will give you what you want. And that's just what he did.
In a very ingenious way, you can think that minus h tau is h times I times tau.
Mm-hmm.
So if you multiply the matrix elements by an imaginary square root of -1 in principle, but is it so stupid or not?
No, I don't. I mean, I don't discount any idea. That's why I was saying that this is a great, how to say, topic for people like us to find clever ways of mapping the algorithms we are used to and the things that we want to compute on these systems. So it's, I would explore that. I would have to think about it, but yeah, one can consider other clever ideas.
Other questions? Yes.
The proton beryllium scattering.
Yeah.
There are many data points. Can you give us some hint what is reliable, what is less reliable?
Okay, so there are data points that are direct experimental results. For example, the Young-Hans, they really directly measure this. But then there are also data points that come from Coulomb excitation, and then they extract the dipole part. So for example, these purple points, they are Coulomb excitation. And in fact, you see, they don't see the E2 and the you know, M1 resonances because they were. So, you know, there are some data that these what we show are those that have been considered during the evaluation process. What I want to say is that for a long time, the data of Young-Hans were held to a high standard. And this evaluation, and in part also the evaluation of Daniel Phillips with the Hello EFT, they were very much driven by this data because there are many of them and the error bars are small. But the problem is that if you look at this sort of like universality curve, let's say, that we found, it appears that the data of Young-Hans are discrepant with each other between the low energy and the high energy. And they seem to be actually, you know, if you weigh them by the number of data points, you get a more unbiased fit. So the jury is out there. It's always difficult to make a judgment about experimental data.
So how did you choose the...
Please use the mic.
How did you choose the 250 point?
No, this is just one example. So this is an example of the curve that you get when you plot the S factor at zero energy as a function of the same S factor at 250 kiloelectron volts. But then we took all, you know, we repeated this, we did a fit for each of these energies between, you know, between 0 and 1.5 MeV. And we took all experimental data in all these ranges. So we have, you know, a bunch of these fits, and we use them to then extract what experiment would tell you that the S factor is. And this is useful because, you know, typically as an experimentalist, you feel that you need to go as low energy as you can. And then what happens is that, this is not fast enough, there you go. What happens is that the lower you go in energy, the larger your bar gets, because, you know, that's life, the counts are small. But what our correlation study suggests is don't kill yourself to go to low energy, stay at higher energy where you can have lower error bars, and then let's use this correlation to extrapolate to zero energy. So it's just a suggestion.
Further questions? Alejandro?
Sofia, when you calculate the case of two neutrons, no, with the quantum computer, which is the magnitude, the quantity you calculate? What do you calculate?
With the quantum computer or with
So
you're asking classically, what do you feed to the quantum computer, or what the quantum computer gives you?
What the quantum computer gives?
The quantum computer will give you the occupation probability of the states at the end, you know, after a while, right? So you have the computational states to which you have mapped your spin states. So 0, 1, 2, and 3 will correspond to different spin states. So it kind of tells you how much are the two neutrons in, let's say, the triplet state. How much are they in triplet state?
Okay. My question then is, because we are in universal conference, no? If you use different, we know that the scattering length of the two neutrons is big and is less dependent of the form of the potential. You use, I saw that you usually the northern chiral potential, which include the two contact interaction plus the pion exchange, but you can use only the two contact interaction without the pion exchange using what is called the pionless form.
Yes.
So if you use different forms of these processes, you will obtain using the quantum computer the same result or different results?
Okay. now don't want to trip myself. The problem is that, so one reason for which we took the pion full, or the chiral, is that you really get the spin states coupled in a non-trivial way, right? You get the tensor force, right? So that will couple the various quantum states. I don't know where I'm going here, okay? And so basically what happens is that these guys will mix, because otherwise if your qubits the probabilities don't mix with each other, they will just keep oscillating on their own. And so it was less interesting in a way, but I have to think about this more profoundly to your question.
Okay.
I admit that.
Just a silly question. What is your code in quantum computing? Is it a shape of microwave field, or?
Yes, that's yes. So basically, as theorists, what we do is to solve that time evolution optimization problem. So we basically compute the unitary that we want to realize, and then we do these optimization problems to find which are the pulses, and then we feed them to through a computer, through a control electronics that sends the microwave pulses to the QPU, and then they give us back the data that then need to be analyzed.
Okay.
So you kind of turn a little bit into an experimentalist.
Chris?
Yeah, I was struck by the number you quoted for the number of CPU hours for the DT fusion reaction.
Yeah.
200 million.
Yeah.
That's pretty impressive.
It's actually, it's worse right now because we use GPUs right now. So if you translate how much that means in CPU hours, you get easily to 500 million, per year or more. So we are competing with lattice QCD these days. Yeah.
So what takes the most time in that calculation? How can I understand that number?
What takes the most time, I don't want to go back there, but what takes the most time is, you have this part of the basis that is this microscopic cluster. Okay, what takes time is compute the matrix elements of the Hamiltonian with these microscopic clusters, because they need to be anti-symmetrized. This is what we call the kernels. And those are really, involved. The heavier is your projectile, the harder it is to compute them.
Thank you.
Other questions? Okay, Sofia, you told us that there's a bright future at the horizon. Do you have any idea about the time scale?
I don't. I mean, you have seen this is a toy problem, but the thing, Winfried, is that right now the question is not. So let me be clear. I'm not against the universal quantum computing that others use, right? The idea to use a basis set of elementary gates to implement your unitary. That's where we want to end up, but that requires error correction.
So I think we can close the morning session and go for lunch.